Hi, so in our last lesson we learned about torque, and if you remember, torque is going to be a measurement of how effectively a force causes rotation on an object. So today we're going to continue that same line of thought and think about what other factors are going to impact how an object rotates. So the main idea that we want to focus on today is going to be called the moment of inertia. And I'll walk through what exactly the moment of inertia is. Before we do that, I want you to imagine a scenario where we have like a ramp. So I'm going to try to draw a 3D ramp here. Hey, pretty good. All right, not the best, but okay. So on this ramp, imagine that you have three different objects that are going to roll down. So you have a filled in, like this is a ball, so this would be a sphere that is completely filled in, so a solid sphere. You have like a hula hoop, so this is just the outside ring. And for our third object, let's say we have a cylinder. So I'm not sure if I'm going to be able to draw a cylinder, but imagine it's like a coin, a really big coin. Okay. I want you to imagine if all three of these are going to roll down, which one do you expect to, and they all weigh the same mass, which one would you expect to get to the bottom first? Okay. And you might think that they would all reach the bottom at the same time, because if they're the same mass, they're the same size, in theory, they should all get to the bottom at the same time. But there's something important that we need to consider, and that's the distribution of material that makes up the mass. So, for example, with a sphere here, say the mass of all three of them was 10 kilograms. This 10 kilograms is going to be distributed differently than the 10 kilograms that is just located around the outside of this circle, and also differently than 10 kilograms that's located in a flat cylinder, or a flat cylinder shape. Okay, so the way that those molecules, that mass, is distributed is actually going to impact the way that they move. And specifically, it's going to impact the moment of inertia. If you think back to when we talked about linear stuff, we mentioned inertia in relation to Newton's laws, in that we said an object at rest stays at rest unless acted upon by an outside force. An object in motion stays in motion unless acted upon by an outside force. So inertia is that tendency to stay in whatever state you're in. If you're moving, you keep moving. If you're stopped, you stay stopped. Okay? Moment of inertia is that same idea, except we're talking about rotation. So how likely are each of these things to stay in their the format that they already are in? Okay? Are they going to stay stopped, or are they more likely to start rolling? And this now is going to get a little bit complicated, because there are different equations to figure out how likely they are to move depending on their shape. We have a basic equation that we're going to use for this, which is moment of inertia, which is I, equals I as in inertia, equals the mass times the radius of the object squared. Okay? Now, that being said, this equation applies to a hoop. So say our hula hoop right here. That would be the equation for it. Other shapes have different equations. So for example, the moment of inertia for the sphere here is actually 2/5 mr squared. So you see it still has the basic mr squared, but it's a fraction of that equation, okay? And the cylinder here, the equation for that is 1/2 mr squared. So before you guys start freaking out on a problem with this type of question, or on a question with this type of problem, I would give you a chart that told you the equation or the relationship for each shape involved. So like the shape and the equation, sphere equation, cylinder equation, rod equation. Okay, so you don't need to like memorize all of the different shapes and their equations for moment of inertia. You just need to know that it does change depending on the shape. So to get a better idea of this, I'm going to walk you through a problem and how we would use these equations to figure out how likely something is to spin. Okay? So let me clear the screen. And our question is up here now. So a simplified model of a twirling baton, like what you spin for, I don't know, football games? Who uses batons now? But of a twirling baton is a thin rod with 2 round objects at each end. Oh. It went away a little bit. Hold on. Okay. So we have a thin rod with 2 round objects at each end. The information that's given to us is that the length of the baton is 0.65 meters. And the mass of each object is 0.30 kilograms. And it wants you to find the moment of inertia of the baton if it is rotated about the midpoint. So if it's spun right here. And then after that, what is the moment of inertia if it is rotated about one end? Okay, so if we're spinning from the middle here, all we need to do is think about, okay, what shape is that going to make if we are spinning this object? And this is a little bit hard to conceptualize, but if you look at it, if you draw the picture again, so we have a weight here, we have a weight here. We're going to ignore the mass of the rod because it's not given to us. So if we're spinning it clockwise, let's say, all of our weight is actually spinning, if this is our axis of rotation, all of our weight is just on the outside of this shape. So really, this is the same as if it was a hollow like hoop, because there's no weight on the interior here. So our equation for a hoop is that basic I equals mr squared. For the problem of if we're spinning in the middle, the radius is going to be half of the total length given. So that's 0.33 meters. And the mass of the object, the mass for one of the objects, let's start here, is going to be 0.3 kilograms. Okay. So if we do that, then we're going to get mr squared equals 0.3 times 0.33, so we get I equals or initial I equals 0.033 kilogram meter squared as a unit. But remember that that is only for one of these weights. So if we imagine this as a solid object, a solid hoop, really the weight includes both sides. So we're going to double that number. So our moment of inertia for, if we're spinning it about the middle, is going to be 2 times 0.0033, or, sorry, 0.033. So I will be 0.066 kilogram meter squared as the unit. Okay? Now we need to think about this in a different way, because it's asking, what about, all right, now we're not spinning about the middle, but our axis of rotation is just this end point. So now we need to rethink this picture, because we have our place where it's spinning, and then it's spinning like this. That's a terrible picture, but you get what I'm saying. So it's going to be a bigger circle, a bigger hoop. We're going to use the same equation, but now instead of a moment of inertia being, a radius being half the length, the whole rod is going to be the radius. So we go back to our I equals mr squared. But now the mass is going to be still 0.3 because it's just this one weight that's contributing. So 0.3 times, now it's 0.65 meters squared. So our I here equals 0.13 kilogram meter squared. Okay? And then the last thing is, which is greater? So we have, if we're spinning it about the middle, this is the moment of inertia. If we're spinning it about the end, this is the moment of inertia. So which one is less likely to spin? Which one's going to be harder to rotate? And the answer would be the longer, spinning it from the end, would be harder to get started spinning. It would take more effort. Okay? So as you go through these problems, the main thing is to try to figure out, all right, what shape am I working with? And if you have the shape that you're working with, then the equations are pretty easy to work through just using algebra. All right? Thanks.